We'll go deeper on aggregate expenditure. In our aggregate expenditure model, we keep hitting this equation. Y equals C plus I plus G plus X minus M. Now here I put G, X, and M in gray, because for now we're going to set those equal to 0, just to keep it really simple to start. Begin just Y equals C plus I. The others are 0, they drop out. For consumption, the main determinant is disposable income. Look, a lot of households are living paycheck to paycheck. If they have more money, then they spend more money. If they have less money, then they spend less money. Some households are saving, but some households are dissaving, which means accumulating debt or drawing down their savings. Now, sometimes expected future income is relevant. I mean, it may be sensible if you're a student, take out loans, because you anticipate once you graduate, you'll have a higher income. Your consumption today might be higher than your income, because you anticipate that in future your income will go up, and then your consumption will be lower than your income, and you can pay back some student loans. And then start saving for retirement, down the line. There are a lot of complicated dynamics. I don't want to say the simple model is absolutely the truth. It's just a simple little model. But we'll locally approximate consumption as a linear function of disposable income. Model consumption as A plus B times Y minus T plus E. A and B are parameters. E is just the error term. We'll relegate all that other stuff into the error term. A is autonomous consumption, the intercept term. Then, next step we ask, okay, how much does consumption change when income goes up by $1? We call that the marginal propensity to consume. Economists love the word marginal. We talk about marginal everything. Everything's on the margin because rational people think on the margin. Our models depend on rational agents making decisions on the margin. So B is the marginal propensity to consume, MPC. We assume B is going to be between 0 and 1. In aggregate, if income goes up by $1, then consumption will go up by less than $1, but it'll go up some. Now, it may be the case for particular individuals, their own MPC could be outside the 0-1 interval, but that's not generally going to be the case. The other part of our really stripped down simple model is investment. That's the I there. Firms estimate a future amount of profit from their investments and compare that with their borrowing costs, determined by interest rates. Even the simplest business needs some financing. For example, if you're going to have a little side hustle selling stuff online, then whatever stuff you're selling has to get manufactured first, probably somewhere in China. Somebody doing the manufacturing will want to get paid first. So even if you're completely successful, everything you contracted to make gets sold. Hey, wonderful, that's good news. But still, the fact remains the stuff is sold later in the process. Your supplier wants to get paid before you actually get the revenue. Some sort of financing is going to be needed. I mean, if this is a side hustle, you just started up, then when we say financing, we mean your personal credit card, or maybe friends and family. As businesses get larger, that financing is going to be more regularized, but still the cost is the interest rate. Investment is largely determined by interest rates. We haven't put those in the model yet, so for now we're just going to treat investment as given some level. Our very simple model has a bit of algebra. You can see why I wanted to strip out a bunch of realism, just keep the math a little bit less scary to begin. The first line restates our assumption consumption is a linear function of disposable income. The second line is investment is given to some level, determined by interest rates. Not in this model. There's a different model about how interest rates determine investment. Leave that for later. We set G equal T equal X equal M equals 0, so we don't get things too confusing too soon. The aggregate expenditure equation has Y equals C plus I. Substitute in. So our equation is C is A plus BY, because T is 0, that drops out. Investment is just I naught. Collect terms, Y minus BY is going to be equal to A plus I naught. Divide through, get Y equals 1 over 1 minus B times A plus I naught. That term, 1 over 1 minus B, that gives us the multiplier. If B, the marginal propensity to consume, is something like 80%, then that would imply the multiplier is going to be 5. This idea of a multiplier is commonly used. If for some reason investment rises, then people get paid. Hey, good news. But what do they do when they get paid? They go out and buy stuff. If I get paid a little more, I'm happy. I'm going to go out and spend a little bit of that money. Maybe 80% of that money. Maybe I'll save 20%, but the other 80% becomes income for somebody else. Somebody else gets 80 of that increase in investment, and they in turn spend that raise, and that churns through the economy. It generates a multiplied impact. It's common to hear these discussions in policy questions. The algebra is just giving a function for that convergence series. We want to graph this, and we put aggregate expenditure on the vertical axis and y on the horizontal axis. Y is the production, aggregate expenditure is the spending. In equilibrium, aggregate expenditure has to equal y, which is just another way of saying supply has to equal demand in equilibrium. That happens in this graph on the 45-degree line, where the horizontal axis value equals the vertical axis value. The green line there is C equals A plus BY. The red line is aggregate expenditure, which is C plus I. So it's a parallel shift upward. The equilibrium value is going to be where that red line intersects the 45-degree line, the dotted line. That will be the equilibrium value of output. As the marginal propensity to consume, which is B, gets larger, then the green line would be steeper and the value of the multiplier would be larger. The multiplier is a change in y divided by the change in I. In the graph, you can see the change in I on the vertical axis, and the change in y is a change in the equilibrium value of y, that's on the horizontal axis. Because of the slope of the line for C, delta y will be larger than delta I. That's just how the multiplier works.